frequency response analysis. What is the difference between time domain analysis and frequency response? But what happened to differential equation? Differential equation is very, very important because all systems, all physical systems in the world are represented by differential equation. Without that, we can't do anything. That's why the mathematicians spent more 200 years they spent solving differential equations. Because each type of differential equation has to be solved in different way. We struggled a lot in UG class to solve differential equations. So they spent 200 years to solve differential equation. Means all systems in the world are represented by differential equations. One of the best invention is Fourier transform. He transformed the given differential equation into algebraic equation. Solving algebraic equation is not that much difficult. Simultaneous equations you will solve while solving circuits theory. If many algebraic equations are there, by matrix method you will solve. Cramer's rule, something you will use to solve the different algebraic equations. If it is algebraic equation, easily you can solve, you can find the solution. But if it is in differential equation, it is very difficult to solve. So if you take transform, Fourier transform, the differential equation becomes algebraic equation, that's why we can easily solve. Again, we have to take inverse Fourier transform because we do not know, we cannot understand in frequency domain what is physical variable in frequency domain. That's why again you have to convert in time domain, so you get the result. So that is the advantage of Fourier transform. But in control system, we cannot apply Fourier transforms because Fourier transform we cannot apply on unstable systems. But most of the systems in control system are open loop unstable but closed loop stable, or will deal with unstable systems. Many unstable systems will deal. That's why we cannot take Fourier transform. That's why they are taking Laplace transform. That's why it is defined in Laplace domain. Laplace transform can be taken in Laplace transform can be taken for unstable systems. Unstable functions can be converted into Laplace domain. That's why we are using Laplace transform in control system. Once again, the same question: what is the difference between time domain analysis and frequency domain analysis? What is the relation between time domain and frequency? F equal to, what is the relation between time and the frequency? They are inversely proportional. So, what is the advantage? If it is in infinity, it will be at 0 in frequency domain. In 0 in the frequency domain, it will be at infinity in time domain. So, we are inverting that way. That's why if you want to see the steady state response means we have to see in frequency domain. We have to see in frequency domain, we will get steady state responses can be easily seen. Because of that, they are handling things in frequency domain. Two reasons. One is algebraic differential equations are converted into algebraic equations, and steady state responses can be conveniently seen in frequency domain. Because of these two reasons, we are handling the problems in frequency domain. What is frequency response? In electronics lab, how we are obtaining the frequency response of a common emitter amplifier. All UG students will do that experiment. Common emitter amplifier, frequency response of a common emitter amplifier. They will vary the frequency. For each frequency, they will find a steady state value, not transient value. What is the steady state output they will find? They have to take for different frequencies. Finally, they will mark the magnitudes for different frequencies. They will get frequency response. It will be like this, a trapezoidal type waveform. It shows that if frequency goes beyond certain value, amplitude is diminishing. Similarly, if you decrease the frequency, then also amplitude diminishing. But in control system, all are low pass filters. But it is not trapezoidal, it will be like this. It will be like this. So low pass filter. All control system components are low pass filter. That's why is not trapezoidal, it will be, and low frequency side it has constant gain. Main gain is not decreasing as frequency decreases, approaches. What is frequency response? We'll give sinusoidal input. In the output side, what is the amplitude we'll measure? What is the phase shift we'll measure? So that if you plot between frequency and amplitude, that is called magnitude response. If you plot between phase shift and frequency, then it is called phase response. Why we see that? Why we are plotting the amplitude and the output amplitude and output only we are plotting. The input signal is A sin omega t. R of t equal to A sin omega t is the input signal. It is given to the system, but we are varying the frequency from 0 to infinity. We are varying the frequency from 0 to infinity. For variable frequency, we are here. You see that R of t is the input signal is A sin omega t, but output signal C of t is B sin omega t plus phi. The phase shift is there. But note that in both cases, the frequency omega is same. Why? Because of this OLDWC system. Ordinary linear differential equation with constant coefficients. In other words, linear system. If it is linear system, then only the input signal is input signal frequency and output signal frequency will be equal. A sin omega t. We know that CFS in the frequency domain, CFS equal to. What is GFS? The mathematical model of the system. GFS is you have to think about system. The mathematical model of the system multiplied by that is input signal of the system. GFS multiplied by RFS is nothing but CFS. In frequency domain we can multiply. In time domain we have to do convolution. That is also another reason why we are going for frequency domain. Whatever convolution is there, if you get into that frequency domain, it is simple multiplication. That's why we are multiplying GFS and RFS. But RFS is a sinusoidal input signal. Laplace transform of sin omega, A sin omega t is A omega divided by S square plus omega square. That's why the CFS, the output signal equal to, the output equal to A omega divided upon S square plus omega square multiplied by G of S. How we will find the inverse Laplace transform? How to find C of t? We have to do partial fraction and R. If you do partial fraction, first for R of S you are getting these two. Because A omega upon S square plus omega square. If you do partial fraction, you will get these two terms. Plus partial fraction of G of S. But the G of S is responsible for transient part. R of S is always existing. R of S is input signal. Why transient is coming? Because of the system. Because of system, you are getting transients. So transients will die out after some time. Transfer function part is responsible for transient part. So if you do partial fraction, the input part is and the partial fraction of transfer function part responsible for transient response. But frequency response is steady state response. That's why you can ignore it. We can ignore that. Therefore, steady state response of CSS, steady state response equal to K upon S plus J omega plus K upon S minus J omega. That's all. Where K is K star is complex conjugate of K. That and all. So, we have to find the inverse Laplace transform. For that, we are doing all these manipulations. Finally, we have got C of t equal to this. C of t equal to function of G of J omega. What is G of J omega? So far we have seen transfer functions are G of S. But I am writing here G of J omega. What is G of J omega? Replace S by J omega. That is called frequency transfer function. That is called frequency transfer function. If you replace S by J omega, then it is called frequency transfer function. Both are same. Instead of S we are substituting J omega. So here G of J omega multiplied by some exponential functions. This is the response of the system. You don't need to explain all this mathematical part. That you can see in the book. If you further simplify this, we got C of t equal to this. The function of G of J omega multiplied by some exponential function. Next. simplify, we are getting C of t equal to A g of j omega multiplied by sin omega t plus phi of omega. It means the output signal is some magnitude function. Magnitude also function of omega. Already we have seen that in frequency response, magnitude is changing with respect to frequency. That's why it is not constant. Magnitude is not constant, it is function of omega. The output magnitude is function of omega multiplied by sin omega t plus some phase shift is there, that is also function of omega. That is also function of omega. As frequency changes, magnitude changes. As frequency changes, phase shift changes. That's why we can write the output as function of b of omega multiplied by sin omega t plus phi of omega. B omega, the magnitude is function of omega. The phase shift is another function of omega. That's why the output is like this. The output is like this. What is E of here? What is the input here? We are giving sinusoidal signal. Here also we are getting output also a sinusoidal signal, but there is a phase shift is there. Here it starts at 0. Here it is not starting at 0. There is a phase shift is there. There is a difference in amplitude is there. Here amplitude is constant amplitude A, but here amplitude is B, function of omega. Function of omega. So if you here g of j omega, already we know that it is C by R. What is transfer function? G of S equal to C of S by R of S. G of S is the transfer function of the system. It is nothing but Laplace transform of output upon Laplace transform of input. If you replace S by j omega, we will get G of j omega equal to C of j omega by R of j omega. So if you take modulus, you will get G of j omega equal to C of j omega by modulus of R of j omega, and phase also equal to angle of G of j omega equal to C of j omega by R j omega. How we got this? Here, what is B of omega? A multiplied by magnitude of G of j omega. A multiplied by magnitude of G of j omega. A equal to 1. Always we keep A equal to 1. So B of omega is nothing but G of j omega. B of omega is nothing but G of j omega. Here if you see, what is the phase shift? Phi of omega is the phase shift introduced by this system, angle of G of j omega. That is equal to angle of C of j omega by angle of R of j omega. So the output response can be defined by G of j omega and phi of omega, instead of defining by b omega multiplied by sin omega t plus phi omega. Instead of telling like that, I can talk this way. It is nothing but b omega. The magnitude is b omega. In other words, the magnitude is modulus of G of j omega. As omega varies, the magnitude varies. I can simply say, what is the phase shift? Phase shift is angle of G of j omega. Angle of G of j omega. In that way, I can represent. So, frequency response is nothing but the plot of transfer function, frequency transfer function as omega varies from 0 to infinity. Frequency response is plot of frequency transfer function as omega varies from 0 to infinity. What is the phase plot? Phase plot is nothing but angle of G of j omega, plot of angle of G of j omega as omega varies from 0 to infinity, because the output function is function of G of j omega and angle of G of j omega. That's all. So frequency response is reduced to plot of G of j omega and plot of angle of G of j omega. Plot of G of j omega versus omega is known as magnitude plot. Plot of angle of G of j omega versus omega is called phase plot or phase response. Magnitude response or magnitude plot. What is that? Magnitude of G of plot of magnitude of G of j omega. Similarly, angle of G of j omega. If you plot the angle of G of j omega as omega varies from 0 to infinity, that is called phase response. That's all. So we have to plot these two with respect as taking omega as a reference. That's all. That is called frequency response. How many frequency responses are there? What are the variety of frequency responses? That we will see now. What next? This is here we are taking x-axis as omega, y-axis the magnitude is plotted here. Here phase is plotted. This is called frequency response. Frequency response, but x-axis is taken in linear scale. Linear scale. X is taken in linear scale. If you take in linear scale, it is very difficult to accommodate wide range of frequency. That's why the frequency is taken in logarithmic scale. If you take in logarithmic scale, wide range of frequency can be accommodated. What are the various types of frequency domain specifications? What are the time domain specifications? How quickly it reaches the final steady state value, settling time. How quickly it reaches the final steady state value, first time, raise times. That is called raise time. Then overshoot. We don't want to large overshoots. So we are taking overshoot as a measure. What is the overshoot? Then steady state error. Any other time domain? Delay time. How much time it takes to respond for a given input. That is called delay time. So these are all time domain specifications. In frequency domain, there are some specifications. The specifications are resonant frequency. Each system has some resonant frequency. In that frequency, its magnitude will be very high. Its magnitude will be very high. Output magnitude will be very high. That is called resonant frequency. Omega R. Resonant peak. Already I said that for that frequency, the magnitude, output magnitude will be very high. What is that value of magnitude? That is called resonant peak. Cutoff frequency is frequency up to which we can accommodate the response or we can accept the response. Up to which frequency we can accept the response. For example, if the output power is half of maximum power up to one particular frequency, means up to that we are taking. After that we are not considering that system. We are beyond that frequency, we are not considering that system for amplification or some other reason. We won't use that. That is called cutoff frequency. Or 1 by root 2 times. Here it is a low pass filter. Control system is a low pass filter. That's why we will have a cutoff frequency in the right hand side only. We will have a cutoff frequency in the right hand side. At zero frequency, what is the magnitude? We will see. When omega equal to 0, what is the magnitude? We will see. In that, we will take 1 by root 2 times of that frequency is the cutoff frequency. Cutoff rate is at cutoff frequency, what is the slope of that? At what slope the magnitude is decreasing? That is called cutoff rate. Then gain margin, base margin. I will explain the gain margin, base margin in different slides. It's very difficult to explain the base margin, gain margin here. So these are the frequency domain specifications of a control system. Next, bandwidth is the range of frequency. Bandwidth is range of frequency. Here always it starts with omega equal to 0 to higher frequency. 1 by root 2 times bandwidth. Correlation between time domain and frequency domain specification that we are going to see here. What is the correlation between time domain and frequency domain specification? In time domain specification, zeta is very important parameter. What is zeta? If zeta equal to 0, always it oscillates with constant amplitude. If zeta equal to 1, no oscillations. Zeta equal to 1, no oscillation. It quickly comes to the final steady state value. If zeta is very large, system is sluggish, it takes long time to respond. I am having a voltmeter, indicating instrument. In that I am giving input, it will give output after a long time, means there is no use of such instrument. Zeta is very large. So zeta plays very important role. Here, what is the correlation between the zeta and the frequency domain specification that we are seeing here? Here, C of S equal to, this is the system we are considering. G of S equal to omega n square upon s square plus 2 zeta omega n s. That system is considered. What is the order of the system? G of second order. S square plus 2 zeta omega n s. So we can take one s outside the denominator. That's why type 1 system. What is meant by type 1 system? Is if a system has a pole at origin, then the system is said to be type 1. Order means the degree of the S, we can say. Type number means how many S can be taken out, how many poles at the origin, how many poles at the origin or in the denominator, S term, how many S terms, what is the power of S term, that is type number of the system. The closed loop transfer function is, if we take the closed loop transfer function by unity feedback, this open loop transfer function becomes like this, omega n square upon S square plus 2 zeta omega n S, 2 zeta omega n S plus omega n square. That is the closed loop transfer function. That is the closed loop transfer function. If we consider this closed loop transfer function, we are dividing the numerator and denominator by natural frequency omega n square. To convert this into a convenient form, we are dividing the numerator and denominator by omega n square. We got this. This can be called as m e power j alpha. What is this? If you write everything in terms of omega and omega n, what is this? Omega n is constant or variable? Here, omega n is constant, natural frequency. Omega n is variable. Omega is variable. Here it is a sinusoidal transfer function. Sinusoidal transfer function or frequency transfer function. In that, if you want the response means, we will vary omega. But what is the magnitude of g of the omega? We will see. So, if we go to the next slide, this is nothing but magnitude. This is nothing but magnitude. That's why this can be written as m multiplied by e power j alpha, where m is d omega. We have seen d omega, magnitude of the response, that is m. The alpha is the phase shift. Alpha is e power j alpha means what is the magnitude of e power j theta? Irrespective of theta, the magnitude always 1, but angle varies from 0 to 360. That's why this alpha is phase angle. M is magnitude. So if you find the magnitude of this, then you will get this expression. M equal to 1 upon square root of real part square plus imaginary part square. What is the phase? Alpha equal to tan inverse of imaginary part by real part. Go to next slide. So this is another way of writing the given m multiplied by e power minus j alpha. So already we found what is m, already we found what is alpha. So that can be put in this convenient form. If you replace by omega n by u, I am substituting omega n by another variable u. Then that is called normalized frequency. Then we got this form. So m equal to 1 upon square root of 1 minus u square whole square plus 2 zeta u whole square. This is m. This is m. So u is nothing but frequency. You can think that u is nothing but frequencies. Next. In the previous slide, if we vary zeta, we are getting the response like this. Go next. If I am varying zeta only, for different values of zeta, I am varying u. I got this type of responses. I plotted between m versus u. M versus u. In that zeta, for different values of zeta, I plotted. So here, when zeta equal to 0, the amplitude is maximum. When zeta is greater than 0.707, the magnitude is less than 1. Zeta is greater than 0.707, magnitude is less than 1. If zeta is less than 0.707, its magnitude goes on increases. As zeta approaches 0, the magnitude is very high. Very high. So then I got a correlation between time domain analysis and frequency domain analysis. That if I decrease zeta, the amplitude of oscillation increases. Here, if I decrease zeta in the frequency domain, the magnitude is increases. If I decrease zeta, the magnitude is increases at omega r at resonant frequency. So there is a correlation between time domain and frequency domain analysis. So in time domain zeta, there if I decrease zeta, the large oscillations are there in time domain. In frequency domain, as I decrease omega, the m increases. M R increases. So I can find maximum value. Differentiate m with respect to u. Differentiate m with respect to u and equate to 0. Find the value of u. For that value of u, the m will be maximum. So in mathematics, we will find the maximum value by differentiating the given function with respect to the variable and equate to 0. We will find that variable. For that value, the function will be maximum. That way I found when u equal to square root of 1 minus 2 zeta square, m will be maximum. M will be maximum. So the maximum normalized resonant frequency u r equal to square root of 1 minus 2 zeta square when frequency equal to the normalized frequency omega divided by square root of omega n equal to square root of 1 minus 2 zeta square, the magnitude will be maximum. The frequency ur is a real quantity, therefore we get 2 zeta square. It is a real quantity, and this frequency is a real quantity. That's why if it is 2 zeta square is less than 1, it becomes imaginary. That's why 0.707 it becomes imaginary. If it will be greater than 1, that's why it becomes imaginary. This means that for all values of zeta greater than 0.707, the resonant frequency omega is 0 because it will not exist imaginary values. And resonant frequency MR is unity. That's why in control system for low frequencies it becomes unity and constant. This is the reason why there is the low frequency side it is remains constant. Here substitute the value of u from that ur, you will get m. If you substitute the m, u equal to square root of 1 minus 2 zeta square. If you substitute, you will get mr. So I got the resonant peak in terms of zeta. Zeta is the time domain parameter. Zeta is the time domain parameter. Mr is the resonant peak is the frequency domain parameter. I got a correlation. The correlation between frequency domain parameter and time domain parameter is mr equal to 1 by 2 zeta 1 upon 2 zeta square root of 1 minus zeta square. That's all. So how to get this? M is given. M equal to what? Transfer function of given system. Transfer function of given system modulus of g of j omega. Differentiate that with respect to frequency. Equate to 0. You will get the frequency at which the resonance frequency will occur. So substitute that value in the m. You will get this mr. That is in term, it is function of zeta only. It is function of zeta only. But zeta is time domain parameter. But mr is frequency domain parameter. So there is a correlation between frequency domain and the time domain. The resonant frequency is, already we have seen this, resonant frequency is ur equal to square root of 1 minus 2 zeta square. But ur is normalized frequency. I want to know in terms of omega only. That's why substitute ur equal to omega r by omega n. Therefore, omega r equal to omega n square root of 1 minus 2 zeta square. But omega n is natural frequency of the system, that is constant. Another relation between bandwidth and what is the relation between bandwidth and time domain parameters? For that we are taking again the same m, squaring on both sides we got this equation, and finally we are finding roots of this equation. Why we are equating this 1 by 2, we have to see that. Why we are equating to 1 by 2? The cutoff frequency is 1 by 2 times of passband frequency. That's why we are equating this to 1 by 2 times of this magnitude. So now squaring on both sides and simplify, you will get the value of u. Y suffix b. For u, y suffix b is there. What is the relation for this? We are finding the relation for bandwidth. So the bandwidth frequency is omega or ub. Normalized means ub. That's why equating m to 1 by 2 times and squaring on both sides and simplify, you will get ub, that is equal to function of zeta only. Again, square root of function of zeta only. So the bandwidth also can be represented in time domain parameters. So that is the correlation between frequency domain parameter and the time domain parameter. That's all. I want to give the outline only. So what is the derivation done? You can see. So ub is the bandwidth in normalized frequency. The right hand side, what are the functions? It is in zeta only. That's all. So, but C of t, you know, the second order response of system is C of t. I think second unit you have not yet seen. the response, time response of a second order system is C of t equal to 1 minus e power minus zeta omega nt divided by square root of 1 minus zeta square sin omega dt plus phi. Where phi is the phase shift. If you substitute omega d equal to omega n square root of 1 minus zeta square and phi equal to tan inverse of 1 minus zeta square, the maximum peak overshoot is mp equal to e power minus zeta phi divided by square root of 1 minus zeta square. This mp is what? Maximum peak overshoot. In time domain, mp. In frequency domain, mr. So the relation between mr is already we know that in terms of zeta. So mp is function of damping ratio zeta only. Mr also function of zeta only. When zeta equal to 0, mr is infinity. When zeta equal to 0, mr is infinity. Here if you put zeta equal to 0 in time domain, it becomes 1, the maximum value. Otherwise it is less than 1 only. So we got a average. When zeta is between 0 and 1 by root 2, the resonant frequency has a value less than omega n. Half power point magnitude you get if it is less than half power point. 0 to 1 by root 2. If it is greater than 0, if zeta is greater than 1 by root 2, the condition dm by du equal to 0 will not satisfy for any value of omega. It gives imaginary values. That's why it will not give any values. It will not give any values. Already we have seen that if zeta is greater than 0.707, it becomes imaginary. That's why this will not work out. Zeta greater than 1 by root 2 will not work out. These two ranges, when zeta equal to 0, mr is infinity. In time domain, mp is maximum. So that is the correlation between time domain and the frequency domain. So if what is the message from this? Time domain parameters are zeta, that is responsible for quick wasting, that is responsible for settling time, that is responsible for overshoot. So time domain parameter means zeta only. That is, if you see formula for overshoot, if you formula for settling time, if you see the formula for race time, everything is function of zeta only. So time domain parameter means zeta only. But here in frequency domain, if you find mr, it is function of zeta. That's why there is a correlation between time domain parameter and the frequency domain parameter. That is the message. That's why we derived two derivations. One is the relation between zeta and mr. Another one is the relation between zeta and the ur. This is a plotted on the same sheet for mr as well as mp. As frequency decreases, mr also goes to infinity, mp also increases to maximum value. So it has some relation. That's what time domain parameters. Now we go to frequency plots. What are the ways we can plot these frequency responses? What is frequency response? Frequency response is for a system if it gives sinusoidal input but variable frequency. The output magnitude is measured, and if it is plotted, then it is called frequency response. The output response is Bw multiplied by sin omega t plus phi. Bw is nothing but the modulus of g of j omega. Already we have seen. So, if I want to know the magnitude for given frequency means, I have to plot the modulus of g of j. If I want to know what is the phase shift, if I want to know means I have to plot the angle of g of j omega. Because phase shift is nothing but angle of g of j omega. That's why the plot between magnitude, that is omega, modulus of g of j omega, and omega is magnitude term. The plot between angle of g of j omega versus shift, but it can be plotted in many ways. One is called linear frequency plot. In that, x will be already you have seen the x-axis frequency is taken in linear scale, and y-axis the magnitude is taken either in linear scale or in decibel scale, whatever it may be. It is called linear frequency plots. That's all. Then linear magnitude but logarithmic frequency scale. Magnitude is taken in linear, but frequency is taken in logarithmic scale. That is another plot. Linear magnitude versus logarithmic frequency plot. That is called the linear magnitude versus log frequency plot. The third one is Bode plot. Bode plot is both are in logarithmic scale. Magnitude is in decibel. Frequency is in logarithmic log omega. Then it is called Bode plot. then it is called Bode plot. Small correction is there. Bode plot is not actual plot, it is approximate plot. That we will see later. We will see Bode plot. Why it is called approximate plot? We will see that. So Bode plot is approximate. Then Nyquist plot. That is also frequency response plot. Nyquist plot means a polar plot. We can call it as partial Nyquist plot is called polar plot. So polar plot is subset of Nyquist plot. Subset of Nyquist plot. So we can call it sometimes interchangeably polar plot is called the Nyquist plot. Polar plot is called Nyquist plot. Nyquist plot is a plot between if you plot this in a polar chart, if you draw the frequency response in polar coordinate, then it is called Nyquist plot or polar plot. If you draw the frequency response in polar coordinate, then it is called Nyquist plot. Next, Nichols plot. Nichols plot is you will have a chart called the Nichols chart. In that, if you draw the frequency response, then it is called Nichols plot. What is Nichols chart and Nichols plot? We will see at the end of this session. This is polar plot. This is polar plot. To understand the gain margin, phase margin, if you use polar plot, before teaching Bode plot, it is better to teach polar plot. Because we can understand the gain margin, phase margin from polar plot is better than understanding from Bode plot. That's why it is better to explain the gain margin and phase margin by using polar plot is very, very important. You see, this is nothing but a polar plot. How polar plot is plotted, we have to see. Already we have seen that magnitude plot is magnitude of g of j omega as omega varies from 0 to infinity. What is phase plot? Angle of g of j omega as omega varies from 0 to infinity. Here we will remove the x-axis. Take these two y-axis and plot the response. That is called polar plot. Plot taking phase and magnitude. Plot taking phase and magnitude. We are not taking omega. We are not considering omega. Here you cannot find omega. What is the value of omega from the chart? You cannot immediately find. You cannot find it. So if you take this response, how I got one point here at this point, what is the magnitude? Modulus of g of j omega. What is the angle? So here, what is the magnitude here? The magnitude is a. I am pointing the point at which I am pointing is the magnitude is a. What is the angle at that point? 180 degree. 180 degree. At this point, the angle is minus 150 degree. At this point, the magnitude is 1.2. Sorry, 0.8. I can say 0.8. Here, the magnitude is 0.8. Angle is minus 150. So, in this way, if I know various angles and magnitudes, I can draw the polar plot. For each value of omega, you will get angle of g of omega one value. Say phi. So, I am getting set of A's, set of phi. I will take each value. Here, the magnitude is A, angle is 180 degree. Angle is 180 degree. I got this point. Another point here, the magnitude is A1, angle is 150, minus 150. So, I got this point. Like that, for each magnitude and phase, if I plot, I will get this response. I will get this response. That is called polar plot. So, it is plotted between magnitude and phase, no omega involved. But how we got magnitude and phase from omega only? For the magnitude and phase corresponds to one particular omega. So those pairs are taken. For that, if it is plotted, then it is called polar plot. So in that, if you increase gain of the system, what will happen? If you increase gain of the system, what will happen? I am having one transfer function g of s equal to k divided by some function of s. That is the given transfer function. In the transfer function, I am slightly increasing k from 1 to 2. I am increasing the k from 1 to 2. What is the change in the magnitude plot? Earlier, this is the magnitude plot for k equal to 1. If I draw this, again I am finding the frequency response for k equal to 2 means it will be that shape will be identical, but it will be like this. If k equal to 3 means shape will be identical, but the plot will be like this. If k equal to 4 means the shape will be identical, again it will increase like this. So, if k increases, there is no change in phase. There is no change in phase. What is the angle of K? Angle K is a real number. 0. That's why it will not affect the phase angle. That's why the shape will not affect, but the shape will be retained, but it will magnify. But instead of changing K, I have a facility. If I change some particular component, there will be a change in phase shift only. Let us assume there is no change in K. But if I adjust some component in the system, some part of the system is modified, then there will be change in phase shift. Let us assume. I can do. In a RC phase shift oscillator, in the RC component, if I change some capacity value, there will be a change in phase shift. So I can adjust phase shift only. Without changing gain, I can adjust phase shift. So if I adjust the phase shift, what will happen? There is no change in magnitude, but there will be a change in phase. So magnitude at this point is 1 because it is unit circle. Here the magnitude is -1 plus or minus j at this point. Here what is the magnitude? 1 only, but angle is different. If I increase the angle, what will happen? This point will move on this unit circle. If I increase phase. If I decrease phase, what will happen? This point will move down. Now the angle is 150 means if I increase the phase shift, this point will move upward. So then the shape is modified. If you further increase, what will happen? This point will come here means the shape will be by adjusting phase only. I am not adjusting gain. I am adjusting phase only. This point will come here. Therefore, the plot will be like this. I am not adjusting gain. I am adjusting phase only, but the system is passing through -1. If the response is passing through -1 means the poles are on the James axis. The frequency response is passing through -1 plus or minus J0 means the poles are on the James axis. In time domain. That's why I gave those introduction and all. So if the poles are on the James axis means it is not stable system. Always it is oscillating. But amplitude is constant. Always it is oscillating. In control system we don't want such systems. So that is the maximum limit. After that the system becomes unstable. If you further increase, the system becomes unstable. So the stability of the system can be derived from this phase plot, the frequency response, Nyquist plot. If the response passing through -1, the system exhibits sustained oscillation. If it does not enclose this -1 plus or minus J0, the system exhibits stable response. If it encloses this -1, if it goes beyond this -1, the system becomes unstable. What is gain margin? Suppose I am standing on 7th floor. Here I am standing on 1st floor. That's why without minding about this height I am going and coming. Suppose this platform height is about 7 floors. Whether I am dare to move on this? Never. I will be safely away from 4 or 5 feet because my height is about 5.5 feet means I will be safely from the edge. I will be away from 5.5 feet. Even I fall, I won't fall down there. That's why that is called margin. Always margin is required. There. Here no problem. Even if I fall, no problem. So a margin is required in the system. Why that margin is required? Always we have to tell the students which is not in the book sometimes. Then only the students will respect us. So something won't be in the book, then we have to tell. Why the margin is required? You see in any control book, they won't mention. Why gain margin is required? Here it is constructed, this building is constructed, those are all pillars. How they arrived at the dimension, they will calculate the dimension may be 1/4 of this only, or 1/6 of this one. I am not civil engineer, maybe 1/6 or 1/4 of this one. That much pillar size is sufficient for this building, but they constructed 4 times higher than that. Why? Factor of safety. Even unexpected thing happens, it should be strong enough. That's why 4 times stronger is constructed. Like that, in control system, we are assuming that all coefficients in the differential equation are constants. But if it is not so, what will happen? If the coefficient varies, because of that, the poles may go to right hand side. The poles may go to right hand side. If the poles go to right hand side, means what will happen? System becomes unstable. So, I should not be very close to j omega axis. I should be away from j omega axis by this much magnitude. In terms of parameter, not in terms of any other thing. In terms of parameter, in terms of k, or in terms of zeta, or in terms of something, I should be away from the edge. I am away from the j omega axis. What the gain margin and base margin is required? Because in practical systems, you are thinking that you may think that my gain is constant. My gain may not be constant. If we talk about some other thing, I may not be interested. I may sleep. So my gain is not there. My gain is 0. If I talk about control system, my voice will be very high. So here gain is very high. So depends upon the situation. The gain of the system will vary. The parameters of the system vary. Parameters means constant coefficients of differential equation or coefficients of s in the transfer function. The coefficients of s in the transfer functions are constants we are assuming, but it is not so in practice. Even if it varies, the system should not go to unstable. Like this factor, like pillar. Like pillar, it should not go to unstable. That's why some margin is required. How much margin we require? Normally they will put a margin of gain margin of 50% or 0.5. Again, gain margin of 2. Factor of safety will be 2. In decimal scale, 20 log 2. In linear scale, twice. If you increase the gain by 2 times, then only it becomes unstable. Similarly, phase margin they will normally put to 30%. This 30 degree they will put. Here it will be 120 degree. If I increase further 30 degree phase shift, it will pass through -1. So the system becomes in the verge of instability. It continuously oscillates. So we can make the system unstable either by increasing the gain or by increasing the phase shift. So while designing the controller, how much margin you should provide so that if any undue change is happening, it should not drive the system to unstable state. That's why how much margin we have to put. That is called gain margin and phase margin. For that, gain margin is if I increase the gain by this much. So here what is the magnitude? 1. Here the magnitude is A. Here what is the magnitude? 1. To make this A to 1, what is the gain required? 1 by A. If it, suppose A equal to 0.5. A equal to 0.5. I want to make it 1. What is the gain required? 1 by 0.5, that is 2. So the gain margin is 2. That's all. If I make the system gain equal to 2, the system becomes unstable. So the margin is that much. I am safely this much away from unstable. Safely this much away from instability. Are you able to understand? That is called gain margin. Gain margin is 1 by A. Here what is that? Modulus of G of j omega equal to A. At the phase crossover frequency. Go to the previous slide. One more point I have to explain. Here, what is the magnitude here? 1. What is the phase here? 180. If it satisfies both, then the system becomes unstable. The verge of instability, it exhibits continuous oscillation. If you further increase, it becomes unstable. So at the -1 plus j0, the magnitude is 1, phase is 180. Here, the frequency at which phase equal to 180 is phase crossover frequency. Each point is different frequency. Are you able to visualize that? Each point is different frequency. We are substituting omega in the transfer function. We are getting different modulus of g of omega and angle of g of j omega. So each point is different frequency. At particular frequency, it crosses -1 plus j0. So that frequency is called phase crossover frequency. It crosses the 180 angle. That's why it is called phase crossover frequency. It crosses this magnitude 1 at particular frequency. At this frequency, it crosses this -1. That's why it is called gain crossover frequency. That is called gain crossover. It crosses the gain limit. That's why gain crossover frequency. Here, it crosses the phase limit. Phase should be 180. gain is 1. So it crosses 180, that's why this point is called phase crossover frequency. This point is called phase crossover frequency. Here it crosses magnitude, that's why it is called gain crossover frequency. Now we understand what is gain crossover frequency, what is phase crossover frequency, what is gain margin. Now we have not yet seen that phase margin. Phase margin, what is that? How much phase I can introduce so that this point will come here. How much phase I can introduce so that this point will come here. If this point come here, the system will be in the verge of instability. If any further increase, the system becomes unstable. Because it is already in sustained oscillation. Can you understand that? So phase margin is how much phase shift I can, further phase shift can be introduced in the system. That is called phase margin. Gain margin is how much gain I can introduce in the system. For that, we have to find the magnitude at 180. That's why in Bode plot we are seeing the magnitude when it crosses 180. That's why in Bode plot we are seeing the phase at 0 dB. One, if we take log is what will be? Log of 1 equal to what? The base 10 0. So at 0 dB, what is the angle we are seeing to find the phase margin? Phase margin is 180. That's why that angle is subtracted from 180. So this much margin is there. Here the angle is 180. Sorry, angle is 150. So to make this system unstable, up to 180 it has to come. 180 minus 150, that is equal to 30 degree. Therefore, phase margin is 30 degree. So the gain margin and phase margin must be explained with the polar plot. So here only we can explain if gain alone change, what will happen. If phase alone change, what will happen, we can explain. In Bode plot it is not possible. Phase margin. What is phase margin? When it crosses unity magnitude, what is the angle we have to find? The angle of G of J omega we are finding. Angle of G which we are finding, that is equal to 5. Therefore, phase margin is 180 plus that value. It is minus 150 in the previous case we have seen. 180 minus 150 equal to 30 degree. Therefore, phase margin is 30 degree. Gain margin is 1 by A in linear scale. In logarithmic scale, 20 log 1 by A. The gain margin is 20 log 1 by A. 20 log 1 by A equal to what? Minus 20 log A. 20 log 1 by A equal to minus 20 log A. So we have to find the gain at 180 degree. For that we have to take 20 log.